Last week we talked about power laws and origins of scaling, right? How do we get power law? Why do power laws happen in nature? Okay, by what processes? And just a quick summary. We said when we have a phase transition, right, we get power law. So what is the power law in phase transition? Somebody remembers this? What is a phase transition? Phase transition. Water to ice is a phase transition, right? You know this, right? It's you,
yeah.
You're kidding, right? You want to. So magnetism. What is a phase transition?
Magnetism.
Magnetism?
Yes.
What is the? I don't know.
From paramagnet to ferromagnet.
Ah,
right?
okay.
How do you get from paramagnet to ferromagnet?
I don't know.
You cool down the magnet, right? So if you have
we didn't get to this in the.
yeah, okay.
We left in the second lecture.
Okay, I understand.
It was too much.
So just to very briefly, if you take a piece of iron and you heat it up, okay, you make it basically it loses its ferromagnetism and it becomes a paramagnet. Okay.
Okay.
So how do you get it back to becoming a
so you could
ferromagnet? You cool it down, right? So that's the phase transition there.
Okay.
What is the power law that we get there? When you think about the Ising model, what happens at the critical point? So you have when the Ising model is at a higher temperature, the spins
only pointing in the same direction.
Yeah, but they only feel each other as neighbors, right?
Locally.
But locally.
So when it moves from locally to...
Yes, when it moves from local is basically the paramagnet, and you cool it down and suddenly and you are at the critical point, and now the spins feel each other over longer distances, right? So you have long-range correlations which follow a power law. Okay, that's the reason we get power laws in phase transitions and in criticality. Self-organized criticality, what was this? Famous example we studied?
Sand pile.
Sand pile, yeah, right. The sand pile, but the sand pile was not really self-organized criticality.
Yeah.
It was the rise, basmati rise. Okay.
Right.
Earthquakes is self-organized criticality phenomenon. What is in astrophysics? Flares, okay? Sun flares are self-organized criticality phenomena. These processes of multiplying random numbers, we didn't talk much about it. It's a process, but pretty boring, right? You just multiply random numbers. Preferential processes, what was this? Remember this? Rich gets richer, okay?
Oh.
So somebody who already has money, for him or her, it's easy to make more money. For somebody who's poor, it's difficult, right? And this way, you get the power law in wealth. So somebody in Israel who already owns 2 apartments can easily buy a 3rd apartment. Why? Because he doesn't pay rent like all the other suckers, right? He saves his or her money and he buys they buy another apartment. So they get richer and richer. Somebody who doesn't have an apartment pays all his or her salary on rent, and you will never get an apartment. Sorry to discourage you, make you depressed, but this is the rich gets richer phenomenon that
the
makes
mafia effect, right?
power.
The mafia effect, right?
I can also call it like this, but don't want to enter into these details. Sample space deduction process. What was this?
With the pasta.
Yeah, breaking spaghetti, right? It's a sample space reducing process. By turning, twisting the spaghetti, I reduce the sample space, then I can break them easily. Another one is life is a sample space reducing process. Okay, with every day you're living, you reduce your sample space. Sounds very depressing, but it is like this, no? When you were young, you could become a Mozart, you could become a Ronaldo, everything, and now you're stuck with physics. Okay, but you can still become a professor or go to high tech and earn a lot of money. But it's difficult now at this stage to become a new Usain Bolt. Okay, so that's because we reduced our sample space too much. So we had here this example of a die, right, with that you throw, and every time the number that shows you take out, and everything above you take out from the die, and this way you reduce the sample process, and what you obtain is a power law with a slope of -1, was called Zipf's law, and this is where we stopped last time. And today I want to spend a bit more time on these two things here, percolation and fractals. And let's start with percolation. These are the famous books. They are very much going into detail, which we don't need. Just if somebody is interested in, you're welcome to get them here in the library and read them. But what is percolation? Somebody knows? How do you drink the coffee? You know what is the coffee? You have a funnel, you put the sugar inside, spoons or 1 spoon of coffee, and then you put it more, right? And you don't know? This is how I made coffee when I was a student. You don't think, oh, very good. So, pour boiling water on the coffee, and then you see on the bottom the coffee. Okay? This is calculation. Water calculates the coffee. We have here some little situation thing, because it's nice to visualize models. Now you see it, right? So I set up the model and water through it. Okay? Water through the. I have to close the light here. I mean, not much water dies here, right? You can see this. And you see all the water goes through. All the water goes through. What is the end result with your coffee? It's terrible. It's just brown water. It's no taste because it doesn't have enough interaction with the coffee powder, so you get just not tasty coffee.
But this is not the This is not percolation by definition, right? This.
It is motivation for, this is percolation by definition. What you're hinting to is the model, how we model percolation, okay? But this is this is what percolation means. You go through a media, okay?
Okay, but it's not a deterministic process.
This is actually deterministic. But you're hinting to how to model it. We will talk about this in a moment, okay?
Yes, okay.
This is just the motivation now. I want you to get a feeling for percolation. And so everybody agrees that this is not tasty coffee, and everybody agrees that shaking. No. Maybe shake. No, but it will not help much.
Mix.
Hmm?
Mix.
No. What do they have in the corner? What do they do? Have you looked at it, or you just look at the telephone? Meanwhile, they make the coffee, you just look at the emails. And how do they do this? Exactly. They put coffee inside their this I don't know, this device. Yeah, then they take it and connect it to the machina, to this device. And what does the device do?
How do we tread it like?
No, it puts steam through it. Okay,
Yes.
so it's also you hear it also, right? So this is pushing steam through the coffee. As a result, you have what? No. What do you have in the end as a result?
What do you mean?
You have coffee with higher caffeine, right? Because it was pushed through very small grains, and it's more dense, right? So this is good. So much about coffee. Yeah. So everybody gets motivation of calculation, and it is a very nice model for phase transitions. So let me explain. So everybody agrees that this, what we looked at the coffee grains and stuff, is a disordered material, right? And how can you study phase transitions? You can say, okay, I can imagine instead of sending water through coffee powder, this is like sending an electric current through some material, you know, and now I design the material in a way that the electric current is going through. Then it's a conductor, right? And if it's not going through, it's an isolator, right? You just have to find a way how to manipulate the material. You can have ferromagnet, paramagnet, superconductor, conductor systems, everything that has two components, and you can model some kind of phase transitions by this would work. Also, if you think about it, spreading of epidemics or forest fires, okay, instead of having water going through a coffee grain, you can say this is a virus going through the population. So how do you have to put your population that they don't get infected by the virus? Easy answer, we did in COVID, we lock everybody up, right? Then there's no interaction between them, they cannot get infected. So that's a very powerful framework to model such two-component systems and phase transitions. Now, Gil, we are coming to what you mentioned. So how to model it now, right? What to do? I think the easiest way to explain it is by looking at a square lattice. You have a square lattice, and imagine now you have a grid on this square lattice, okay? Little squares, okay? Here you have little squares all over. And now you go from each little square to the next, and by doing so, you throw a die, or you choose a random number or something, right? And let's say you choose a random number between 0 and 1, right? And when you are below 0.2, you occupy this little square, and if not, you just leave it empty, okay? So here we don't occupy, here we occupy, okay? Here we don't occupy, here we occupy, and so on. So, of course, if you have only a probability of 20% to occupy and 80% to not occupy, you get a very sparse image like this, right? There's not much, I mean, not many clusters. As soon as you have two squares, neighboring squares that are occupied, you connect them, right, by this line, by this link. So, and you do this for the whole square lattice, and you get a picture like this, and only some isolated clusters. And now, if you get back to this insulator conductor image from before, if you want to send a current from here to here, it would not flow, right? There's not enough material inside that it could flow. However, when you repeat this process, but now you do, actually I didn't show you before, there was a critical point at around 0.6 that the water goes through the coffee, right? This was at 0.6. I don't know if you paid attention, I went to 0.8, everything was flowing through, and I went below 0.6, then it got stuck, but 0.6 is exactly the point where it goes through.
What are the connected lines?
Here?
No, the first.
Yeah.
So circles with connected lines.
Yes, you connect them when you have neighboring squares that you occupied, you link them, okay? You just link them.
Why they are linked?
They are just linked because they are neighbors. So when you have two occupied neighboring squares, you link them. This is just
You mean like a successive
you put a wire between them.
Okay, so you have dynamically you can go from one another. This is what you mean?
No, I mean you go through this. You do this once, right? You go through this process of occupying, not occupying, and then in the next step you say, I look where do I have neighboring cells that are occupied, and then if I have them occupied, I link them. I put a wire.
Okay, so you have an underlying intrinsic parameter in your model.
My underlying parameter is just the probability that I occupy. The probability that I occupy, and afterwards I just link what is the result, right? The resulting occupied cells I link when they are next to each other. Is clear?
No, I'll ask you maybe in the.
So when you, I mean, occupy and not occupy is clear, right?
Yeah.
And so you imagine this picture without the lines, okay? Now in the next step, I go through each. Actually, I go to each occupied square, and I look around to the south, to the north, east, and west. Do I have a neighbor? Okay. If I have a neighbor, I link myself to him or her.
Okay.
Okay. That's it. That's the only.
But if you don't have a neighbor,
then I don't. Here, this guy doesn't have a neighbor.
The process is stopped.
He is. No, it's not. It's stopped.
You move and check the other box. Just check each box. You iterate on each box. Either it's occupied.
Yes, but this I do in the beginning. Yes, this I do in the beginning, and the lines I draw at the end.
Yeah.
When I see the result, I see now a matrix of occupied and non-occupied cells, and I only connect a neighboring occupied. That's it. Okay. When I do this with a higher probability at 0.59, of course I have more occupied cells, right? And now I have something very interesting happening, that I get a cluster, okay, of occupied cells that goes from one end to the system to the other end of the system. It's called the infinite cluster. Why it's called the infinite cluster?
It has infinite amounts of points.
No, you have a fixed number of points. But it's infinite because I could repeat the same thing for a square that is twice the size. Okay, and I get again this cluster. So this cluster basically is, I mean, could go to infinity, right? And I put my system size to infinity. So this is exactly happening at 0.59, and this is my critical probability. Okay, so at the critical probability, I get an infinite cluster. When I'm above this critical probability, and this is now conducting a current, right? This is conducting a current from here to here. But I can also say, okay, I occupy with 80% probability. Then I get something that is almost completely filled, okay? And this also like in the analogy of conductor or non-conductor, this would be a metal because you have high conductivity here in this kind of structure. Okay, is this clear? What? Obviously, here the critical point is 1, right? So here the first occupy 1, and we have the third point. And then another important thing is the rate function. This is the mean number of sides, the same cluster, and this is R on any occupied side. So how to calculate this? So this will be very easy. My side also one calculation first. You not occupy the side, but you occupy the side. This is one of side calculation. You occupy the side. And one calculation occupies the side. or make a honeycomb. There are all kinds of different geometry, and you can see, okay, different probabilities. So here you see the line. So it's clear. The line is for half, right? And if you take instead of the side, you take the point, right? You get a different. What
They are close.
They are close, but
Correlated.
the bond is always smaller. The critical probability for the bond is always smaller. Why is it like this? Why is it like this? Again, this critical probability gives me a measure when current is flowing, right, from one side to the other.
Yeah, there is less area that is covered with.
Exactly. You have much more options. Okay. Look at this. You have many more options. So you reach your critical probability earlier than if you just take occupied sites. Okay. That's the reason. Good. Now let's look at this a little bit in more detail, and we say, okay, we define an order parameter. It's called P infinite. This is the probability that a particular site belongs to the infinite cluster, right? And I plot here this probability P infinite over the probability that I choose, right? So this is the fat line. Okay, ignore the other lines, the fat line. It is 0 until PC. Why it is 0?
No core.
There's no infinite cluster until PC. So the probability to belong to something that doesn't exist is 0, right? At PC, suddenly the infinite cluster appears, and I have a big increase in the probability. So this is a linear plot. If I plot this logarithmically, it is a power law. Okay, it is a power law. Good. So this is P infinite, and obviously when the probability is 1, then everything is occupied, and P infinite is 1, right? Obviously. Now I have here some other lines. This is this Xi. Okay, this Xi. What is this Xi? Xi is the correlation length. The correlation length is the mean distance between two sites on the same finite cluster. Basically, it gives you the size of the average size of the finite cluster. Okay. Why does it behave so strangely? Yeah. P increases and Xi increases here, and it diverges at PC. Why it is like this? It's the average size of the finite clusters, right? The finite clusters obviously grow with P, right? They grow. It's also a power law. They grow like a power law. At PC, I have an infinite cluster, so it diverges because it's infinite. That's also the reason why the infinite cluster is called infinite, because Xi diverges. But what happens here? I increase P and it drops. Very strange. Why is this?
Because the infinite cluster is getting bigger.
Yes, and what happens? But this
So
measures not the infinite cluster, it measures the finite cluster.
The finite cluster is getting smaller.
It eats up all the, so the infinite cluster is eating up all the smaller guys, right?
You get
So-
many more options. You get many more options. Once you've just reached the criticality, you can spread out.
Yeah,
to
you
the
can
sides.
also say this, yes. But here, basically, it shows you that finite clusters are dying out. Okay, and that p equal 1, you don't have finite clusters. Everything is the infinite cluster. Good. So we have understood this. The behavior, I told you, is a power law. So if you look at P minus PC, it behaves like a power law. P minus PC, so this increase here is characterized by P minus PC to the power beta. The behavior of Xi is characterized by P minus PC to the power of another exponent minus nu, okay? And you can also take another measure that is similar to the susceptibility in magnets. I told you we have a lot of magnets today. So the susceptibility, and this gives you another exponent, minus gamma, okay? So something like the size of the average size of the finite cluster. And now the important thing is the following, that these exponents, they are called critical exponents. They are happening at a critical point. Critical behavior near the transition. They are universal. Okay. Before I showed you the table with PC depending on the lattice, right, and on the kind of calculation. If it is whether it is side calculation or the bond calculation, it was a different PC. These exponents, they don't depend on this. They are universal. Okay. They are universal for calculation. They only depend on whether you look at a chain 1D system or you look at a 2D system or 3D system or so on. Yeah, this is also a second order phase transition, as you see. And yes,
mathematically speaking, the critical point, it's a discontinuous point. It's not differentiable. The function is not differentiable at this point.
Yes.
So if you look on the neighborhood of rho C, the critical point, the left side and the hand side are different. That means at this point, if you are at this point, it's standing, nothing happens. In order to reach to the power law,
yes,
you have to necessarily you need to be above the critical point, even in liter. Otherwise, if you are standing on the critical point, there is nothing.
What do you mean there's nothing? There's exactly the...
Well, this is a point, the critical point.
Yes.
What happens when you stand on the critical point?
When you stand at the critical point, so this means that you are exactly, you try to run a current through some lattice, right? And you cannot succeed, and here suddenly you can.
Exactly at the critical point,
yes,
you're going to pass it.
Yes, only at exactly at the critical point you start observing flowing current. If you want to think about, like, in this conductor insulator picture.
Okay.
Yeah. And then, of course, it kind of explodes because you have many more options, right, for the current. And there's also a relationship. You can derive it, but it's not so important at this point, that these exponents, they are related and just depending on the fractal dimension that we are going to learn today. So the D is basically the geometric dimension minus the fractal dimension, and this times nu is equal to beta. But this is not so important, just for you to have seen it once. And now I want to show you, give you a taste how powerful calculation is in order to study, for example, magnetic phase transitions. Okay, so just compare these two pictures. Here we have a magnet, a ferromagnet, and a paramagnet. So, as we said before, when you take a piece of iron at a high temperature, it's a paramagnet, right? you cool it down, reach the critical temperature, which is the Curie temperature, right? And then you start to have an increase in magnetization, right? So in this domain, it is a ferromagnet after below the Tc. And so if you write it down, it's T minus Tc to an exponent beta. Okay, it's a different beta than this beta, right? But it's called beta because the magnetization very much behaves like T infinite. Okay, here. And you can also do it for the susceptibility. So you would have something like you go to Tc, and then you get a explosion in susceptibility when you reach the critical point, and when you go beyond Tc, you increase T further, then you have this decay, right? Because it's paramagnet now. And this is very similar to percolation. What is the difference here?
Minus to the left.
This is symmetric and this is not symmetric, right? And this is not symmetric. Once I had a deep understanding of it, but I forgot. But it had something to do with the magnetic domains, right? They are. It's not the same whether you reach. I mean, here you basically destroy the magnetic domains, and here you have the magnetic domains still, and this causes the asymmetry. I have to look it up again why it's like this. Somebody remembers how this law is called here? This 1 over T decay of susceptibility with temperature.
So the susceptibility, the last graph, is not reversible. This is what you mean?
No, it's reversible. It's you have it's reversible. It's you have this hysteresis.
Okay.
You can always go reverse it. So no, it's called this 1 over T decay is called Curie-Weiss law. And just for you to remember. And so, having talked about this critical exponent, and I told you for percolation, it doesn't matter how the system looks like, they are all the same, no matter if you have squares or triangles or whatever geometry. Also for magnets, when we have three-dimensional magnets, they have the same beta. Okay, it's independent of the lattice or type of interactions, and but Tc and Pc, so Tc for magnets and Pc for the percolation, they depend on the details of the system.
Ronnie, I think you have more options in the higher T.
You have more options in
higher
T
of temperature.
Yes.
You have many more temperatures. that
Because you
can
don't
manage.
have domains anymore. Yeah, I think that's the reason for this asymmetry. Good. Here a couple of what are the values. I mean, what's interesting is here you get a somehow some number, right? Ordinary looking number, and here you get something like this. So indication that these values can only be obtained yet by simulations, right? So this you can calculate analytically. Here you have to do simulations, but interestingly, when you are over 6 dimensions, you can again calculate analytically things. Okay, that's very interesting. The more dimensions you have, the easier it gets to calculate. Can you imagine? Yeah, and for magnetism, you also have
So in low dimension, you have no analytical.
Not for 3 dimensions. 3 and 4 dimensions, you have to do simulations. As far as I know, I'm not
No analytical solution. There's no
not for
rigorous analytical approach.
No.
Okay.
You do simulations, but when you are above 6, it somehow works. Once I knew it, I forgot. You know, if you don't every time use it, but it's not so important for life. Okay, I succeeded to live a couple of years without knowing exactly how it is derived. Just for you to keep in mind, right, that dimensionality is important here. Good. So there are also other structures, just briefly I want to mention to you, that keeping this picture from sending a current from one side to the other, you have what is called the backbone. Okay, so the backbone includes all bonds that carry the current. When you send the current, this is what carries the current. It's basically the bonds of the infinite cluster. The dead ends are also part of the infinite cluster, but they don't carry current, right? So a dead end is, for example, where do we have a dead end? No, I don't find the dead end. But it would be something like this maybe, okay? So maybe these are dead ends here. So the current, it's part of the infinite cluster, but doesn't have a current going through. Here, these red bonds, these are the only connections that run the current. When you cut them, you destroy basically the infinite cluster and you don't have current flowing. And plugs are the parts of the backbone left after removing the red bonds. For each of them, you can calculate a fractal dimension that we haven't learned yet, but just for you again to that you have heard about it. Okay, it's not not critical. And also you can. I mentioned it in the beginning, you can use percolation in order to model spreading of diseases. Okay, so you can imagine you start with something like this. You have here 5 people. So the one in the middle is infected and can is infected by himself and is contagious, right? And he has 4 neighbors, he or she, and one of them is immune because he got the COVID vaccine, and 3 of them are not. So now you have a probability of P that he or she can infect the others, right? And then in the next step, so this one already got sick, but he's not contagious anymore. He's healing, Baruch Hashem, and but these 2 are infected, okay? And now they can spread the virus to the neighbors and so on. So you can simulate how the virus is going through your system and how much it helps when you. I mean, obviously, if you vaccinate everybody, then the virus will not go, you know. But it's not very cost efficient to vaccinate everybody. So the question is how you vaccinate smartly that the virus cannot go through the whole system, right, and is contained. That's what you can do with this kind of easy models.
We have a critical point for this vaccination?
Yes, but Misrata Priot, they are not using population. This is the physicist kind of simplification. But you can calculate the critical transition here, okay? And but if you don't go to the Misrata Priot, they will laugh about you. Okay, that's not. There are other factors that play a role, but just.
It works also in economic. Like if you're trying to sell something, there is a critical point.
Yes, right. You can. It has a lot of applications, and as what I said in the first lecture, when we talked about complicated versus simple models, you remember the spherical cow. You can look at the spherical cow. So this is the spherical cow.
Yeah.
Okay. It helps you to understand the mechanisms, and this is what we are interested in as physicists. We want to understand the mechanisms, and all the details the others can deal with, okay, the engineers. But in order to understand the mechanisms, this is good. It's a good, it will give you not exact numbers, but it will give you laws, okay, how certain things relate to others. So it's not so stupid, okay? It's a good model to learn stuff. That's it about percolation. Any questions? Otherwise, we go to the next topic. Good.
When one thinks of percolation, what do you think the best intuition in one sentence? When you think of percolation, what is the main thing that one focuses on?
When you ask me what percolation is, and the first thing that comes to my mind is drinking coffee.
Okay. So just the way the water interacts with the grain?
It's how you percolate through something, and if you have if you are at criticality, you reach to the end of the system. If you are above criticality, then you reach very easily to the end of the system. If you are below criticality, you don't reach there. Everything else is mathematical details.
Oh.
Okay.
But if we think as a physicist on dynamical systems like Hamiltonian systems, that so you have you could have percolation in Hamiltonian systems, right? Or
Yeah.
depending on what, on the potential.
Oh, you ask me too much now. You mean? I mean, the best percolation works with is phase transitions between two components. If you look now at a particular example, I don't really. I mean, one has to look more carefully in this. If you tell me now some Hamiltonian and ask me if you can apply percolation there, I don't know. I need to think. Not so straightforward. But if you have Hamiltonian, you can solve it analytically. So why do you need to do simulations?
There are Hamiltonians that we cannot. Not necessarily.
Oh, okay. Yeah. But then you have tricks to do some approximation. Okay, I don't know. If you have a particular example, we can talk about it.
Okay.
I don't have now. Good. Next is the last thing on the list that generates power laws in physics, right? Where we find power laws in physics and mathematics. And these are fractals. Okay? And very broad introduction. Fractals were developed in math as a alternative to Euclidean geometry. Okay, so you have Euclidean geometry that we learn in school, and you have fractal geometry. Euclidean geometry, you have straight lines, triangles, and circles, and squares, and whatever. But hardly anything in nature looks like this, right? So in nature, you have fractal structures. So a tree is not a triangle. Mountains are not cones. Clouds are not spheres. Who said this? One of the pioneers of fractal geometry, Mandelbrot. Okay, Mandelbrot in his preface of his famous book on fractal geometry, he writes, fractals are the rule in the universe. Shapes which are not fractal are the exception. I love Euclidean geometry, but it's quite clear that it does not give us a reasonable presentation of the world. Mountains are not cones, clouds are not spheres, trees are not cylinders. Okay, I wrote trees are not triangles, but never mind. Neither does lightning travel on a straight line. Almost everything around us is non-Euclidean. Okay, so what does this mean? What is the special thing on fractals? When we look at most laws in physics, we have some, especially in solid state physics, we have this translational symmetry, right? We have ordered systems where the atoms are sitting on their places, and we have a constant that tells us how far they are apart, and everything has a scale, okay? So the scale that is characteristic of the lattice. However, when we are in fractal geometry, we do not have a particular scale, okay? When you look at a picture of a broccoli, you don't know, is this a big piece or a small piece? And I just zoomed in, okay? When you are when I give you a picture of a crystal, you would know it, right? Because the crystal has a fixed length scale. So we don't have a fixed characteristic scale. We have something is called scale invariance, one aspect, and the other aspect is self-similarity. They are related, right? So one piece looks as the other piece. One smaller piece looks like the bigger piece. This is self-similarity. So self-similarity, scale invariance are the basic properties of fractals. So we don't have a characteristic length scale. And yeah, that's basically what is important about fractals. Yes?
How you define the length in such a geometry?
Yeah, that's a good point. We will talk about it in a minute. Because how you define the length relates very much to the fractal dimension.
Okay.
So we will talk about it in a minute. So example is a tree does not have a characteristic length scale, but basically in the tree you find all kinds of length scales. You have big branches that almost are of the order of magnitude of the whole tree, but you also have small parts of branches that are on the order of leaves, right? So all kinds of sizes are present. And here's an example. I told you about the Romanesco broccoli. I haven't seen it for a long time. Usually they have it around Pesach. Very tasty. And if I show you this picture, you cannot tell me. This is a picture 5 centimeter times 4 centimeter or millimeter. It's impossible, right? Scale invariant. You cannot tell me this computer firm, is this is this here a part of a leaf, or it's the leaf itself, right? Because when I zoom in here, it looks exactly like the big one. So you don't know at which length scale you are. Another example here from chaos theory. You remember the logistic map? Very famous in chaos theory. It can tell you something about predator prey behavior, but we don't have time to go into it. But this logistic map has a lot of applications in science. Maybe I will put you on Moodle. I put you a nice YouTube video where you see where in nature you find the logistic map. But when you zoom into particular points in the logistic map, it all the time looks the same, right? It's amazing.
You mean after the purification point?
Yes, you have to zoom into a bifurcation point, and you recover again the logistic map.
Okay.
So it's amazing. And so I told you that Mandelbrot made a big fuss about fractals, and he wrote the first book on fractal geometry. But fractals were known already 200 years before Mandelbrot, and one of them was who described fractals was Georg Christoph Lichtenberg, and a German mathematician, and he described these kind of figures that are called Lichtenberg figures, okay? And he said, ein Teil sieht aus wie das Ganze, a part looks like the whole. So you already understood when you zoom in, you get the same picture again. So these are called Lichtenberg figures. So Lichtenberg figures, so fractals were called Lichtenberg figures at the beginning, and later only called fractals. And you get these Lichtenberg figures. I have another little movie clip that is showing you this discharge pattern. I hope you can see it. Yes, maybe. Good. So what you have here is a plexiglass. Where's better here? Charged with 2.5 million volt. Okay, so from here to here you have a potential difference of 2.5 million volt. And now this guy here, he is hitting the plexiglass with a nail, okay? And then you see it, so he introduces a kind of a fracture in the glass, and then you have a discharge pattern that spreads through the whole object. So look at this. Here he hits. It's amazing, no? And you see how you have everywhere current. It looks like a thunderstorm, a little thunderstorm. So this is a Lichtenberg figure, it's a fractal. Okay, it has the same geometry as what you see in the thunderstorm, the lightning. So these are Lichtenberg figures. And you also find fractals in chemistry. If you look at the copper deposition from some solution of copper sulfate or mangan oxide layer, they form all these kinds of nice, beautiful fractals. And
so self-similarity is a necessary condition
yes,
for this geometry.
Yes.
And it's defined infinite times.
Yes. In the perfect sense, of course, in nature,
yeah.
In the mathematical sense, it's infinite times, but in nature, of course, you have the maximum and the minimum length scale, right? So, in between which you don't know, it's really self-similar, but when you get to the borders, it's not anymore.
But it's a necessary but not sufficient condition?
No, it's necessary.
Necessary, okay.
Necessary condition that you have self-similarity in scale invariance. It's necessary condition for fractal. So, question is, why did nature choose fractals? Okay. Also, I forgot to mention our organs. The lungs, for example, are fractals. Okay. If I show you a picture of my lungs at a particular magnification, you will not be able to tell me at which magnification this picture was taken, right? Because it looks, you have all these tree-like shapes in the lungs. Also kidneys, all these blood vessels in the kidneys, they have a fractal-like appearance. So the question is, why did nature choose fractals? Let's take the tree, for example. Why a tree has so many different length scales? Okay, I already wrote it there. Because it is more resilient against storms, right? Why would this be? You can also see when you look after a strong wind in the forest, the trees that usually get broken down are the kinds of trees that do not have many branches. Okay, and this is because what happens? A wind is not blowing all the time with the same strength, right? It has an oscillation, right? And if this oscillation hits the eigenfrequency of the tree, because the tree only has one length scale, so it can easily gets it into resonance and it breaks, right? But when it has all kinds of different length scales, it will not get into this condition. So that's one aspect. There are many other explanations why nature chooses fractals, but this is something that is easy to understand. History of fractals, I told you already. Lichtenberg talked about it, but only in the last 30 years we really made progress because we needed the computer to do simulations and to produce these nice fractals like the Fern and look at fractals like the logistic map. And also what is interesting is that fractal geometry is much closer to the computer because the computer also works in this recursive way, right? So it's so Shlomo Havlin used or usually says that it's easier to plot a fractal with a computer than a circle. It's not quite like this, but it gives you the big idea. So let's look at some examples of fractals. First of all, we distinguish between two types of fractals. One is deterministic. This is the mathematical fractal, right, where you have self similarity to infinity, basically. And you have random fractals. That is usually what we have in nature, right? Okay. And we will have examples from both of these types. Deterministic fractals or mathematical fractals, ideal fractals, you can say, show self-similarity on the whole on all length scales, and self-similarity is a property, not a definition. Here's an example: the Koch curve, everybody knows it, or the Sierpinski gasket, right? Sierpinski, everybody knows this, right? I don't need to talk about it. Everybody knows how to make a Sierpinski gasket. You start with your filled triangle, and then you take out the middle, and then you have three small triangles. You take out the middle again, and then and so on. So this is how you get a Sierpinski gasket, and the Koch curve we will talk about now. How to get the Koch curve? You start with a line, and you replace always the middle of this line by this chukchik. Okay, this you know how to say chukchik in English. So by this structure, okay, this incomplete triangle, and then you go to the next. So you have now this line. You put here this incomplete triangle. You have this line. You put and so on. Right? You build in every iteration. You build a more and more complex structure. And now, Gil, we come to your question. And what is the length scale? What is the length of the Koch curve? What is the length of the Koch curve? Anybody?
It should be infinite.
It doesn't look infinite.
It doesn't look, but all the time you add more and more.
Ah, okay, so you have a point. So it depends where I'm looking, right? Well, I mean, you can argue like this, but you can say something else also. How do we measure length? How do we measure length? With a ruler, right? So it depends what is my ruler size, right? So with this ruler I can easily measure this length and this length, but with this one it gets difficult, right, to measure. So I need here a smaller and smaller ruler, and what would happen when I have a smaller and smaller ruler? So this length will be much longer than this length, right? Because I have here all these little pieces. So the answer is it depends on the length of your ruler. Okay. So now let's just go through it to taking different ruler sizes. So if we take a ruler like this, okay, so my ruler is of length 1, then my Koch curve is of length 1, right? Now I take 1/3 of this ruler. So 1/3 is here. Then I can go suddenly inside here, right? So I get 4/3, right? So with 1/3 I get 4/3. When I have even smaller ruler, so that can go inside here. So 1/9 in my original ruler, I will get 16 of this. 1, 2, 3, 4, 5, and so on. 16, okay? 16/9 you get. So the smaller your ruler, the longer the length, basically. So when you write this down, your length, as you can see here, increases by 4/3 to the power n, when n is the iteration, right? And the length of the ruler at the same time decreases, right? It goes from 1 to 1/3 to 1/9, so 1/3 to the power n. This is your ruler size. So how is this now related?
What is n? What is n?
N is the iteration. Okay, if you are at the first level, n is equal to 1, n is equal to 2, n is equal to 3.
But we said that it's infinite, no?
You can go to infinity, yes. You can do this until infinity, but we want to have but it doesn't. There's no change. It all the time changes the same way. You know, the length increases as the ruler decreases according to this law. Okay, and this is related to the dimension of the object. So now we are getting into the direction of a fractal dimension. What is a fractal dimension? But let's first rethink about dimension of an object. Okay, objects that we know from Euclidean geometry. A line, a square, and a cube. Okay, now we want to measure these objects by taking smaller rulers. Okay, here we have a ruler of length 1. Here we have a ruler of length 1/2. I chose here R. R means is the inverse of the ruler length. It's like the magnification, right? So here R is equal to 2. So when my ruler is half the size, or R is equal to 2, in order to cover this square, I need now 4 little squares, right? And I need 8 boxes in order to cover this 3D object. When I am going to 1/3, I need 9. And I need 27 here, right? I need 27 boxes in order to cover the cube. So, so you see that the number of lines, squares, or boxes, this NR, right, scales with R to the power D. So here, when I have 2, okay. When I have, I look at the square, I have, I get 4, right? 2 to the power 2 is 4, and 2 to the power. If I have, if I'm at 3, I have 3 to the power 2 or 3 to the power 3, right? Everybody understands it? Very simple. Okay, or this is when I use R. When I use the ruler, I have to do the inverse, right? It's 1 over ruler size to the power D. So how do I get now my dimension? This is dimension, right? The dimension of the object. Here I have 1, 2, or 3. How do I get D? Very simple mathematics. I do a log, right? I do log n divided by log r, and I get D, right? Or here I have log n minus log n divided by log delta, and I get D. Very simple as this, right? Everybody sees this. Good. So
mathematically speaking, if we think of interactions as like the topology that involves with this geometry that we are trying to build is of sets, right?
Yeah.
Relation between sets. This is how you build it.
Yes.
Mathematic.
Yes.
Okay.
Yes. But with this now, we can get back to our Koch curve, where we, let's say we want to know the ruler. So we have the number of times I can put my ruler on the structure, and I know the size of the ruler, right? This is what we did before. We had here, when the size of the ruler was 1/3, then I could cover it 4 times, right? This is what we got before. So now we can calculate the dimension of the Koch curve. Same formula as we just obtained. And we said we have here 4 boxes, right? 1, 2, 4 lines that cover the structure when my R is equal to 3, or my ruler size is equal to 1/3. And then when we plug this in, we get 1.26. What does it tell us? The Koch curve is more than a line. but it's less than a 2D object, right? Like a rectangular. So, and this D that we obtain there is called the fractal dimension. And the fractal dimension is usually a non-integer. So for most of the fractals, and it's between 1 and 2 for line-like fractals, and usually don't fill the whole area, 2D area, except when you look at this fractal. It's called the piano curves, after the Italian mathematician Piano. How would you construct such a fractal? You start with a square, take out this side, and then you replace each side here by these 3/4 of a square. And here you put it on the lower, here you take the middle one and replace it, and here you take the lower one and replace it by this structure, and then you do it again, right? You take this one and you replace it by this, and so on. So, and when you do this infinite times, you get something that fills out completely the 2D. So the fractal dimension of a piano curve is 2, right? It fills. It's a curve, so it's a curve, actually it's a line, but it fills out the complete 2D space, so the fractal dimension is 2. An example of a fractal dimension below 1 is the Cantor set, named after Ito Cantor. Now Cantor is, he's written with K and E, so this was a German mathematician, Cantor. And what you do here is you take a line, you start with the line, and you remove always the middle of the line, okay? And then, so you do this, and in the end, you end up with something that's also in some books called Cantor dust, okay? When you calculate it, the fractal dimension is less than 1, it's 0.7, 0.8, something like this. Less than a line. Good. So much about deterministic mathematical fractals. Now let's look into nature, okay? Fractals in nature, and a famous example of fractal in nature are length scales of coastline. So the question is, how long is, famous paper was, how long is the coastline of Britain, okay? And what should be the answer?
Depends on your ruler.
It depends on your ruler. Yes, exactly. I cannot tell you if I don't know what is the kind of device you measure the length with. So let's look a little bit at this coastline. Somebody knows from where this is? Which coastline? It's very famous. It's like Arnold Schwarz. No, this is not Arnold Schwarz. It would be more thick. This is me doing this. So, which coastline is this? Very famous. Very famous in American history. Why? First of all, it's Cape Cod, and this is where the first English guys, these pilgrims, arrived in the ship that was called Mayflower. Exactly. So they arrived here, and they said, "Oh, we reached America." And then they walked a little bit, and they said, "Oh, we didn't reach completely." So, I don't know exactly but here they arrived first, and from here they start to conquer the continent and killed all the Indians. So here it started, okay, with Cape Cod, and we want to know what is how to measure the length of this coastline, and we can use the same approach as we did for the Koch curve, and can do the same also for England. This is now England, right? And as Shai said, depending on how long is our ruler. If it is 100 kilometers and I go around Great Britain, I get one length of the coastline. This is here, right? And then I do my ruler, I take a smaller ruler and I get a longer coastline. And I take it even smaller and I get longer. You know, you can do this forever, but it's not important because you're not really interested in the length of the coastline, but in this scaling relationship. Okay, this is the power law. This is the power law, how my coastline scales with the ruler size, okay, with the scale of observation. So, and from here you can now calculate what? So what is this slope here?
Fractal dimension.
The fractal dimension. This is the fractal dimension. This slope is the fractal dimension, and you get it by just doing log n divided by log r, or minus log n divided by log ruler size, delta. It's a little bit cumbersome to do it like this, okay, because with the computer, I had once a student project, and they needed to program this, and it's not very simple because where do you put exactly your ruler? Okay, and when you have things like this, you have, I don't know if you see this, but you reach a point like this, you know, where you have something going inside the land. So where do you exactly stop? Do you stop here or here? I mean, it's not easy to program this in the computer. And so what is used more often, because it is much simpler, is something that's called box counting. Okay, so instead of putting my ruler on the coastline, I put a grid on top of my picture of the coastline, and then I look how many of my squares are occupied by the coastline. So this is not occupied, this is 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 not occupied, okay? So you count how many squares are occupied, okay? And you get a number. Big squares, you have this number of occupied squares. Now you go to smaller squares, then you get more, okay? You get more of these boxes that are occupied. And the smaller you make your box size, the more boxes are occupied, right? And this also, when you plot log n versus log box size, you get here slope, and this is the fractal dimension, right? But instead of having ruler length and length of coastline, you look at box sizes. So you get fractal dimension by log n divided by log box size, and so this is very quickly done by a computer, right? So here you see just marked all the boxes that have anything inside that is, I mean, any occupied box is colored in red. And this way you can calculate now the fractal dimension of coastlines. Okay? Because there's nothing more interesting than this. Calculate fractal dimension of coastline. What do you think are the coastlines? What are the fractal dimensions of these coastlines? First of all, which coastlines do we have here? Geometry, geography. Geography, what is this?
Australia. Australia.
Australia, very good. This? It's a little difficult. Let's do this first.
UK.
UK, right? It's a little bit turned, right? This is Ireland here. This one is
Scandinavia.
Yeah, it's Norway. Okay, Norway, very good. And this one?
Africa.
Yeah, it's close. Which? Yeah, which Africa?
South.
South Africa, our enemies. Okay, sorry. Should not talk about politics. What do you think has the biggest? I mean, what is your estimate on the fractal dimension here? What would be your guess? of which coastline has the highest fractal dimension and which has the lowest fractal dimension? What is your intuition? Yes?
Britain has the highest, I think.
Yeah, why do you think so?
Smallest islands.
Because you have all these little...
like mostly
it's more
coast,
rough.
no land.
Yes, I mean, no, it's not related to the land. It doesn't matter.
No, but
It is related to the borders, right? I mean, if you have a lot of interesting structure in the borders, you will have, when you zoom in, you get more and more occupied boxes, right? So if, so this is among the higher numbers, but the highest has actually Norway, because you have all these fjords in Norway, right? So the more rough a coastline is, the higher is the fractal dimension. So South Africa
So the
has
higher complexity does
higher complexity, exactly. Higher complexity is higher fractal dimension.
But you said that the above picture is less complex, no?
No, this is the most complex.
Oh, okay.
This is the most complex, has the highest fractal dimension, followed by this, followed by Australia, and South Africa has a fractal dimension that's almost 1. Okay? So South Africa is very smooth coastline. And Australia, you see Norway is 1.50 and Britain is 1.25.
The higher complexity, the higher
The fractal dimension, yes. Israel, what would Israel have, which fractal dimension? I let once students calculate the fractal dimension. You can do it easily. Box counting, and then you zoom in, zoom in, zoom in, and you look at box size versus occupied boxes. What do you think that you get?
One.
Similar
Almost
to
one.
Australia.
It's almost 1. It's a 1 point, I don't know whether 1.02 or 1, no, it was 1.02 or 1.03. And you know why it is not exactly equal to 1? Why it
Because
should-
Haifa.
Because Haifa and Akko, yeah, this spoils the perfect number 1, okay? Because you have there some kind of fjord, and this makes it a little bit more complex, so to say, Gil, okay? So otherwise we would be not complex at all. So, right, okay, and we talked about percolation and the percolation cluster. And the percolation cluster is also a fractal. Just want to tell you this, because see, this is the percolation cluster at different magnifications. And you will not be able to tell me which picture is the zoomed in picture of the other. Can you? Actually you can, but it's not straightforward. So how I zoom in, so which is the first picture? Did I zoom in?
The upper right.
This one is the first one,
Yeah.
then the next,
The
Upper left.
Yeah.
this one, and then
Down right.
Down right.
this one, and this one. But it took you some time, right, to see it. How did you decide on it?
I looked it within the inside the black box marked and then checked for the signatures.
Okay, interesting. When I first asked the students 2 years ago, I asked them in computational physics, I showed the same. And this was one day after the Eurovision 2 years ago, and they told me, see it, you have here a unicorn. And then you have here the unicorn, and here you have the belly of the unicorn. So everybody was seeing unicorns suddenly. So I wonder why. Yeah, yes, but important point is it's a fractal, and when you apply here the box counting, okay, you have to do this analytically. Then you get a fractal dimension that in 2D is 1.9. Okay, so it's not completely filled, as you can see. It's not completely 2D. It's 1.9. In 3D, it would be 2.5. Okay, it's the fractal dimension. Good. So let's make a break now. Can we? I guess. Let's do 15 minutes because this is now a new topic. about time series analysis, and this will be also important for when we go to visit the labs, that we know a little bit about time series. So let's meet a quarter to 2. Okay.
May I ask about the fragment dimension?
Yes.
So you have like 1D, 2D, 3D, and the fragment dimension you get by measuring depending on your ruler, right?
Yes.
So if you get, let's say, 2.5 or something,
Yes.
so what does it tell you?
So if you so you have to distinguish between the dimension of the object and the embedding dimension. Okay. So your Koch curve you put in a 2D embedding dimension, and then you calculate the.
So the dimension is how much you iterate to get inside?
No, the dimension is when you how much the length of the Koch curve, for example, scales with how much I go inside. Okay. Or yeah, going inside means how small is my ruler to measure the Koch curve.
Okay.
So that's it. So how the length of the object scales with my ruler, with my observation length, right?
So numbers, what do they tell you about
The number, so the number when it is, you can say for the Koch curve, it's a number of 1.26. So
yeah.
The Koch curve is more than a line, but less than a 2D object.
Okay.
That's what you can say. Okay, it tells you something about the roughness. Okay, so the Koch curve is as rough as the coastline of Great Britain. But the coastline of Norway, which was 1.5, is more rough than the Koch curve. This is what we can say. Okay. When you do in biology, there are people that, not in biology, in medicine, that look at tumors. Mm-hmm. And it turns out that bad tumors have a higher fractal dimension. So they are more rough on the outside. They are more difficult to remove surgically, and a tumor that is very smooth is usually a good tumor that you can easily take out. So you can, based on MRI and CT, you can calculate the fractal dimension, and you can help to estimate how one of the parameters. Yeah. Of course, it's also cool. Blood measure,
nice.
Measures from blood samples and so on. Yes. Yeah. Yeah, it's okay. I will answer you in English.
אז השיעורי בית לא כל כך הבנתי איך הם יהיו. הבנתי שבסוף קורס אנחנו משמיעים לך את המחברת של התכנות שלנו, ואז עשה לנו 80. עכשיו השאלה כאילו מה המחברת תכלול מבחינת השיעורי בית? אתה מעלה שיעורי בית למודל או שזה...
Yeah, so first of all in the notebook you write, it is a summary for yourself, right? So you learned something about fractals today, so what was the most interesting for you to learn fractals?
So I go home, I write down what I think.
What you like, yes,
okay.
what you learned about it, and then we will go to 4 labs.
So this is my question, the labs, we go on our own, or we come here like today and go all together?
No, actually for when you are in university, we will meet there. So it's 2 times in Gonda, we will meet in Gonda.
Okay.
We have some little introduction by the professor that heads the lab, and then we will do 1 measurement, okay, of 1 student. Everybody gets the data, and we'll do some analysis of the data. So,
okay. So the homework it's like the summaries of the lectures.
Yes, summary of the lecture and
some analysis of the labs.
Yes.
And I wanted to ask also, you send the tasks, right? Like
yes.
So there is not much place to volunteer or to do, like all is occupied already. So I don't know what to do. So I wrote myself like in volunteering with someone, and I did like if possible. And like another friend that with me that joined the course today, so it didn't occupy anything because we came this week.
Okay, I
So,
need to check this. I didn't check it.
I wanted to ask if we can do more than one in some tasks, like.
Yeah, everybody should have the option to get 20, 30 points from.
Okay, and there is like limits, or I can just volunteer to do other recordings or something like this.
For volunteering recording, you only get 5 points, and you only have 4 recordings.
So it's
that's the
20.
limit. Yeah.
So I can volunteer to all recordings, or it's like.
No, I think it would not be fair to others.
Okay.
Want to be a
And I wanted to ask about the background. The background is like to give background about the subject.
I will tell you exactly. So if you decide to do background on the Gate Lab, for example, where we are going, I will tell you what to focus on.
Okay.
I didn't put details there.
So just look like it's already occupied.
So I have to check.
If you can see how we can do it together or something. Maybe one will do the presentation and then another.
I need to check.
And the scripts, like they also need to be presented, or the scripts are just for everybody? Like there is a scripting for the FFT and
so someone will do it. Afterwards, we will put it on Moodle, and everybody else will use it in order to do the analysis.
Okay.
He or she will present the script here. Students can ask questions, how to use it, and then you do the analysis of the data, and this will be in your notebook. But you can use what is on Moodle. Okay.
So we have 4 labs. And 2 of them we need to come on our own. Like.
So no, 2 of them.
I'm asking because I'm coming from Ashdod, so it's like.
Okay.
It's like 2 hours.
I mean, you also don't need to come. It's not.
But it's like the whole point.
I think it's the interesting part.
It's
the course, but I cannot make it mandatory because exactly of this reason. So somebody is Nitzan is in the north, and this day his brother decides to shoot 200 rockets, and she cannot come. So I cannot give her minus because she couldn't arrive because of this event. So it's.
But you will like send an email or something, because we have like the מערכות, but I don't know. Okay.
So to the Gonda there's a fixed day, and then we will talk 1 week before. We will coordinate.
Okay.
And I will also write it. I will write some announcement. We meet at this and this time, there and there. And for Shiva and Ichilov, we get
Okay. So this was the main question. This is
organized. You don't need to go by yourself.
Yeah, this was the main question and the homework. This is what I wanted to understand.
Okay, good.
As I understand, the 8 points are just to write a summary of all the course. So, how do you grade that? Like, what do you expect us to write?
אני לומד מדעי המוח.
I want to see
להיכנס לעולם של מחקר חישובי של מוח.
I want to see from your summary
כזה נוצא לקבל כאילו לא יודע, כרגע אני כזה מתעניין בזה. עכשיו כזה הפנית
וואי, איזה קטע.
If you, for
יש
example,
איזה חוקר בווייסמן שנראה לי
ask ChatGPT, write me a summary about complex systems course with fractals calculated, I will notice, and you will not. But if I see that you really thought about it and it has a personal touch, you put some figures, you say, oh, this I liked, and it's kind of feedback also to you.
And I can add things on my own, like that connected.
You can do whatever you decide.
Because there is like
the factor dimension of Israel is 1.02. I just calculate myself, and here it's 1.04. So it was lying, for example.
Okay.
And
יפה, אז מה אתה כאילו...
stuff like this. Yes, I want to, it's something, a summary that I see you have thought about.
Obviously mine, not ChatGPT's.
Yes.
So this is 80%?
80%, yeah.
Great.
But
and the 20, the rest
20 is tasks. So I thought about everybody doing 2 tasks. But now we have so many students. Because at the beginning of the semester there were only 4 students here. So I have to readjust.
But there is the task.
Yes, it's written on the first.
There is like in the Moodle link to all the tasks, and you can write your name, but it's occupied, always occupied already.
I need to search for a task.
So I have to revise the list and send them
Can I suggest something to you, and maybe you can
do some interesting research that's relation to
papers and send you a paper and looks maybe something like this.
Yeah, for example, I just talked to Indi about it. I didn't touch on this application of factors in medicine. When you look at tumors, for example, you can cover the fractal dimension, and based on this, decide if a tumor is easily to operate. Because the fractal dimension is low, so it's very small, or it's more complicated.
נראה לי אצלי זה 14.
לא, כי כל אחד התעדנו על מישהו אחר. היה כזה, כאילו נכון הייתם 4 בנים ואנחנו היינו 4 בנים. יואו. אבל ניב זה חרענית?
So I know that there is
כאילו רק כזה תוך כדי אני כזה חייבת דשים
אותי כאן, רק נדבר יותר חזק ולמצלמה.
תקשיבו, זה יותר בעשור אחורה, זה כזה
it can actually be related to symptoms like depression and even for the heart rate.
אני נעלבתי שמקודם אתה הזמנת את ניטה לשבת כנראה וכאילו התעלמת ממני אפילו לא אמרת לי שלום.
שאת לא אוהבת את
If you find something dynamic, you can relate it to
אוריב וזה לא מדע. אוריב ובעצם. האמת שאני לא בטוח. האמת שבדיוק הייתי סיבת פיג'מה אתה.
היה להם משחק פיג'מה. לא, תקשיבו, זה כזה, הרגע היום חיה את אריאל, היה את היום אחד. כי היו כמה פעמים שאני נסעתי אז לשמשית, זה יום הולדת שלהם.
יכול להיות, נראה לי שלסני לא הייתי אריאל לא היינו.
כי זה היה אצל אריאל תמיד. לא, איזה ישן זה אריאל. אני זוכרת את זה. כאילו דיברתי עם הבן אדם הסוף.
מה? שלום. שלום, פגשתי מישהו שהיה אצלי סיבת פיג'מה.
לא, היינו ממש עצים.
and I can do it in my spare time with this due date.
והם היו קבוצה של בנים אישי.
Because I'm a lot of things.
Yes, the best would be presented when we just talked about it. But if it's not possible, then I know. Just send me everything.
Okay. In literature.
Yes.
זה בטח לשנות של מש"צים.
Okay, good.
כן, מה אתה רוצה? כיתה ט'?
Yes, you wrote already.
שירים? עם המילים או הבנים? אם את לא מבינה שהשקעתי ליום הזה של המתנה, ואז גיליתי שהוא התחיל לצאת עם מישהי חדשה. היה ממש דרמה בגיל 15.
Why we have
נשמע דרמטי?
why can't we get the children from the plane?
לא עונים לי, מה אני עושה?
And then you
זה לא עונים אחרי כמה 5 שעות? צריך שבוע לא יעלה.
וזה שהמסטרנט ששר, אז שלחתי לו הודעה, ואז הוא עושה לי זה מה שהוא ענה לי.
מה הקשר?
אני הולכת
זה שבוע צריך.
התקבלת?
לא התקבלתי, אבל אני יכולה להתקבל. אבל הם לא עונים לי.
say something about
בוקר טוב בכמה ויצמן.
psychology.
לא, גג 3. גג 3. לא, ב3 יש לי הרצאה. נראה לי באיזה 2
Not more than half an hour. Also, half an hour.
בוא נחושק את המרצה.
Yeah. You're relatively free, but not too much detail. It should be on the level that everybody understands it and finds it interesting and can later relate to the analysis we're doing.
And is there a limit how many people can sign up for volunteering at each?
Yeah, actually, Shai, we can only do one. Can we do some video recording on your lab?
3. We can 3.
But is it easy because we only have 3 hours? You know, we have from 12 to 3.
Okay.
Can we do
Yes,
this
of course.
time?
My experiment ran for 1 hour and we are recording 2 people at the same time.
For how long? For 10 minutes or?
1 hour?
1 hour you record? No, this is too long. It's too long.
Of course.
But, no, but to set up the people, it takes you also 1 hour, no?
It will take, I believe, 20 to 30 minutes.
Then maybe it's reasonable. Then we do 2 people, or you do 3 people?
I know, but there are.
But what are you doing? You do 2 people.
I do 2.
So why don't you do 2 people? We do your experiment, but half. Right. 1 hour is too long.
Yeah.
And maybe even half an hour is too long.
It's a lot of data.
Because the other students don't have the patience to do it.
Yeah.
So I think it should not be longer than 15 minutes. And good, I will discuss with you also what the protocol should look like.
Okay.
If we get something meaningful. Okay, so this will be 2, will be not many. It will be MEG will be only also
MEG,
MEG, yeah.
VR and the gate.
Not more than 2 or 3 people because it will take too long.
Yeah.
What like the recording?
For the volunteers for the recording. I need to specify this. You're right. First I thought only 1, but we can do 2.
Okay.
Yeah.
Okay.
Good. Okay. So we get to the last part of today's list of topics, and it's about time series analysis. Why is this relevant for complex systems? Time series analysis. So we have talked about power law, we have talked about what the complex system is, scaling, and now we have suddenly time series. Why it is important?
How certain things then evolve in time? Is a matter to check it.
Yeah, we want to learn something about the complex system, and we can dissect it, right? If possible, but if you think about the human organism, which is a complex system, the easiest is to just measure the signals instead of dissecting it, right? In order to learn how things work. And sometimes you don't even learn much about how it works. So often this is the only way to learn something about the complex system. Okay, to record data from the system and to analyze it. And we have to learn a little bit about techniques, how to kind of reveal these secrets. Okay, here's an example of a time series. Somebody has an idea what this is? So first of all, you see a trend, right? Something that goes up in time. So When it's a time series, the x-axis is always time, right? Obviously, most of the times. And then we have here some oscillation, right? So what could be this oscillation?
Maybe the season.
Season, right? It could be a day and night. Okay. It could be also season. In this case, it's a season. It's summer, winter. Okay. And we have an increase over time, and it is CO2 measurements. Okay. From the 1960s here to above 2000s, measured in Hawaii, and it is going up, unsurprisingly, and we have also this annual cycle, okay, probably related to photosynthesis. It is more active in the spring and summer than in the winter. So the question is now, how do we analyze these data? Okay, and the most obvious is to dissect it. Okay, we dissect the data. We see here, there's an obvious trend, okay, over time, over the many years. You can just take it out from the data, right? We subtract this trend, and what we are left with are the oscillations, okay, summer, winter oscillations. Right, very easy. We have the oscillations, and again we can dissect this. We can take out these periodic trends, and we are left with residuals. Something that is on top of these periodic trends. And what is the big question now? When we are left with this, does this have any meaningful information, right? Is this just noise? This has some meaningful information, right? But it's trivial. I mean, summer, winter oscillation, not much to learn from, perhaps. But the interesting question is about these fluctuations. Is this just noise? Or does it have any useful information? Okay? That's the question in time series analysis. How do we answer this question? And here we want to build on something that we just learned on fractals. And we said in the end here with the unicorn that the percolation cluster is a fractal, right? And how do I prove it's a fractal? It's because I zoom in and I get the same picture over and over again. When I zoom in, I do this with a square, right? I zoom in with a square. So this is why it is self-similar, because I zoom in with a square and I get the same picture. So it is isotropic, okay? I can say that the scaling is identical in all the directions. It's a square, same scaling in x and y direction. So the magnification boxes are squares. Now let's look at the time series. This is a time series, fluctuating like what we saw before, this residuals, but here this is a measurement of blood cell perfusion in the brain. Okay, so you measure the hemoglobin in the brain, and depending on the oxygenation and your blood flow, it is fluctuating like this. And now when I zoom in, I do it differently. I don't zoom in with a square. I zoom in with a rectangle. Okay, so I have a different magnification on the y-axis than I have on the x-axis. So you see here I zoom in. This is my scale on the x-axis, but this is big, right? And but here I magnify only by a factor of 2, right? So it's anisotropic magnification. But I obtain, by doing this, I obtain the same picture, very similar picture. Can do the same again in the next step and over again, but it's not isotropic. Okay, I don't zoom in with a square, I zoom in with a rectangular, it's anisotropic, it's not self-similar, it's called self-affine. When I zoom in, not with a square, but with a rectangular, it's called self-affine. It's anisotropic, scaling is different in different directions. The magnification boxes are rectangles. Good. But can I still use something that I have learned about fractals, because I related this zooming in here to a fractal dimension, right? Can I do the same with time series? Can I calculate something like a fractal dimension of this time series? That's the thing. That's the question. And now it has a different background, because I took these slides from Shlomo Avlin's course, because I think they are perfect. And he explains it very precisely, that if you go in a fractal like the Sierpinski gasket, you scale the x and the y by the same factor, right? But now let's try to model this self-affine kind of time series. How would we model it? We could think about the following. We take a structure like this, or a rule like this, that a line up, maybe it's better here, a line up, okay, is replaced by the same line with this, again it's a chupchik, okay, all the time chupchik. So this triangle kind of shape, okay, and the line down is the same line, and now the chupchik is here. Important word in Hebrew, chupchik, for all the Chinese students. This would be a first iteration. Then I go second iteration, so I take now this structure, I have a line up, and I replace this line up by the same line and this, how's it called? Chupchik, right? Then I have a line down, I replace this line with the same line and the chupchik. Then I have again a line up, chupchik line until here, and then I have here again a line up, chupchik line. Okay, everybody sees it? Good. And then you can do another iteration. So you get something that looks very noisy, okay? Like a time series. But here it's deterministic, right? We just constructed it. So now you see also when I added here in the second iteration, I added 4 pieces in the x direction, right? So in the x direction I added 4 pieces, but in the y direction it only grew by 2 length scales, right? So x grew by 4, y by 2. It's not isotropic, like here it's anisotropic, right? So I can write down the x-axis is scaled by 1/4, 1/2 is the y-axis, and the whole structure grew by 4 pieces, so it's equal to 1/4 of the structure, right? So, and if I write this now with the fractal dimension and the boxes that we had before, we would write the mass of BL, so B times the length scale is like B to the power of the fractal dimension times ML. Okay, so now we have a relationship between the scaling of this object and a fractal dimension. So in reality, this is not called fractal dimension, but one calls it roughness exponent. Okay, and you also look at it quite a little bit differently. You say when I increase or decrease my x, my L in x direction, how does my W in y direction is growing? That's the big question. Okay, and as we just said before, so the W of BL, when I increase L in the x direction, is scales like B, so this factor of increasing the x direction, up to a fractal dimension, I call it here alpha, a roughness exponent times WL at original scale. So let's, if we think about, so the previous example, we had 1/4, okay, 1/4 of the length scale related to 1/2 of the length scale in x direction related to 1/2 of the scale in y direction, right? So 1/4 L is equal to 1/2 WL, and now I can apply this formula from before. So this is equal to B. B is 1/4 to the power alpha. So I have now 1/2 WL is equal to 1/4 to the power alpha WL. I can easily solve this. I take the logarithm and I get alpha equal to 1/2, right? Log 2 divided by log 4. 1/2. So I have now a fractal dimension for an anisotropic structure. And this is exactly what I wanted, right? I wanted to kind of get a measure for my time series. And here I have it. I have a measure for my time series. Another example is instead of, before we had a Chubchik going up 2, I can also say Chubchik and going up 3. Okay? So what would be the roughness exponent for this? Just plug it in. Instead of, before we had 4 on the x-axis, now we have 5 on the x-axis. 1, 2, 3, 4, 5, you see? 1/5. And at the same time, the W grows by 3, right? 1, 2, 3, so it's 1/3. This is equal to 1/5 to the power alpha, WL. I do logarithm log 3 divided by log 5. I get a roughness exponent 0.68. And now let's look a little bit more on this roughness exponent. So alpha was called also H, like Hurst exponent. And so what does it tell us intuitively? What does this give us? If we take random noise, okay, random noise, Gaussian noise, I just do it in MATLAB or in Python. I plot it and it looks like this, and I calculate the roughness exponent at 0.5. Okay, when I integrate fractional Gaussian noise, I get Brownian noise. Okay, just an integral. So, and it gets less rough, right? You see this? This is very rough. This is less rough. Okay, when I integrate, the alpha grows by 1, right? Because I do an integral. So it grows by 1 and less rough. So it shows you that higher alpha is resulting or comes from a less rough structure, right? So if we have, on the next slide we will see some more examples. Also, this is a stationary process. It's a stationary. So stationary numbers, because the variance is not growing over time, right? But here, when I have integrated this, then my variance is depending on the window size of observation, right? Like what we had last week with the power laws, we saw that if we have a power law between 1 and 2 or 2 and 3, the variance is it is never converging to variance, it is always growing, right? Same here. So we have always increase in variance.
What do you mean by integrate?
Integrate? You sum up. So you have maybe you do a cumulative sum. Who asked? You do a cumulative sum of it. So let's say you have your numbers are +1, and plus 2. So 1 and another 1 maybe. So 1 and another 1, and then it goes down to 0. So you would just sum this up. So your time series would be 1 plus 1 is 2. Then the next one here is 0, so you don't grow. And then you have another one, so you add this up, so you kind of sum up the numbers. Okay, this is your integration, summing up the numbers. It's like an integral. And here another couple of examples. Roughness exponent alpha or h is the same, 0.1. Okay, very rough. Very rough. You integrate it. No, this is here. This is the
derivative.
This is the derivative of this, right? So this is here Gaussian, and this is the Brownian motion. Okay, but the 0.1 relates to this one, and here it's 0.5, and here it's 0.9. So when do you get, for example, this Hurst exponent of 0.1? When you have something anticorrelated, okay? Anticorrelated is when you have some negative feedback, okay? What would be a good example of negative feedback that creates anticorrelations? It's a student evaluation every week. In the one evaluation, they say the lecturer is too fast. So then the next week he is slower, and then they ask again the students, and then the students say, now he is too slow. Okay? Then he adjusts, and then he's too fast again, and then he's too slow. So this is how you get a anticorrelation. Okay? Or a thermostat. A thermostat that should find the exact temperature. It is overshooting, it's too hot, then you adjust. Okay? Now it goes down the temperature, it will be too cold. Okay, so this way you get some kind of anticorrelated process. 0.5 we said is random noise. What is an example of 0.9? 0.9 is now positively correlated. What is an example of this?
What you showed us with the seasons.
Temperature data. Seasons is okay. Seasons.
There is fluctuation, but if you measure change occurrence of things during the change, so it's correlated.
It's correlated for the temperature is correlated, right? Temperature is correlated because you have always a high pressure area, right? A high pressure area over Israel means that we have hot temperature today, and with a high likelihood also tomorrow and the day after tomorrow, because of the system is not changing so quickly. Okay, it has some positive correlations. So this would be an example of H of 0.9. Good, so it's between 0 and 0.5, it's anticorrelated, 0.5 is random, and above it's positively correlated. I told you it's called roughness exponent alpha or H. Why it's called H? Because of someone that was called Edwin Hurst, who first worked with this kind of data. So he did exactly what we looked at the beginning. He tried to answer the question whether there is useful information in these residuals, right, that fluctuate. But he did it for a particular application. He was tasked by determining how high this dam, the Aswan Dam in Egypt has to be built in the 50s, right? So when they built it, they needed to know how high do we need to build it that it doesn't overflow. So and he collected, the Egyptians have for many, many years, the water levels of the Nile was recorded because their life depended on it, right? So they have data of this, and he analyzed the data and tried to understand how high the dam had to be built in order that it doesn't overflow. Don't want to go into details, but this very much relates to whether these residuals are anti-correlated or positively correlated. When it's positively correlated, then there's a higher chance that it will overflow, right? Than when it's anti-correlated. So stuff like this he was working on, and in honor of this he got this exponent was named after him. So what is now the technique that we can analyze these data and say whether this is random, this is positively or negatively correlated? What method do I apply in order to calculate the Hurst or roughness exponent? That's the question. And there are a few methods, but we will use what is called detrended fluctuation analysis. One of you will program this and give it to all the others. And what does it do? Very briefly, if you start with your data, you obtain temperature data or whatever, then you calculate the profile. This is the integral I talked about. You just sum up the values. So this is the blue curve that we see here. And then in the next step, you divide your time series into windows, and at each scale in each window you fit a trend to the data, a polynomial to the data. So here it's a quadratic polynomial, right? You want to remove a quadratic trend, so you fit a parabola to the data, and then you calculate in the fourth step, you calculate the difference between the red line, the fit line, and the blue line, and you get the green one. And the green one now, the green time series does not contain trends, right? It does only contain fluctuations, and you now look at how these fluctuations scale with the window size. This is what you are doing in the fifth step. You look at these variances, you calculate the variances for each window, you sum them up, you get for each window a variance, then you take a bigger window, you do the same, and so on and so on. And then your variance as a function of window size scales like s to the power alpha, where alpha is this roughness exponent. Okay? So this is how you calculate, and then you do a log f divided by log s, and you get your alpha exponent. So the one that programs later the DFA, he or she will talk about this again in more detail. Just for you to know how we obtain these exponents, and just some results. People have done this. They have applied DFA to data to weather data. Okay, so you have here weather data, or these are river runoff data. So you basically check the water level of rivers. Okay, and or here these are the temperatures over the ocean. This is precipitation, is the rainfall, and these are temperature data over land. Okay, what do we see here? We see that we see, what do we see? If we look at water levels, okay, we have, I mean, it's all over the map, right? We have from 0.5, close to 0.5, which is random, almost up to 1, right? So all over the map means we have positive correlated data, so the water levels of rivers are positively correlated. They are not random, but it's not universal. It depends where you are. Okay, even when you're in Bavaria, you have something that is highly correlated and something that is correlated very weakly. Okay, let's take rainfall data. What would you say about rainfall? Are rainfall data correlated? Yes or no? Actually, it's already written. Okay. So it's random. Okay, it's around 0.5. 0.5 is that it's random, and this is universal all over. No matter if you're on the highlands, inland, coast, islands, it is random. Temperature data over land, they are positively correlated. Okay, just as we said before, because you have high and low pressure areas. So they make your temperature data correlated. It's not very strong, it's not between 0.6 and 0.7, but it's universal. It doesn't matter where you are, it is quite universal. Also over the oceans, you have positively correlated, you get positive correlations, but here with a higher exponent. Why is this higher? Somebody has an intuition why it is higher than over land? Why did we get here long-term correlations? Why did we get here positive correlations? I just said it.
Because it is no matter where we are.
We get positive correlations because we have high and low pressure areas, right? The weather doesn't change so quickly because we have these high and low pressure areas have to move, okay? And only when it moves out of our region, and let's say we have a high pressure area and now a low pressure area comes, then we have a drop in temperature or increase in temperature. But as long as it moves above us, we have about the same temperature, right? So it's not reacting very quickly, the system. Why do we get, so what does it mean that we have here higher values over oceans? What does it mean? If we said over land, it's not reacting very quickly, so over the oceans, it's even slower. Why it's even slower? Why it's even slower? What does water have that land doesn't have?
Air.
In the winter, you can, when you are going to Tel Aviv in December, it's a little bit chilly, but you can still go inside the sea, right? It's still a little warm. I mean, it has a high heat capacity. Right? Heat capacity is high, so the system is even more slow to change, and that explains why you have higher correlations. Okay, because of the heat capacity. That's the single most important ingredient here. Good. So now we understood how to decide whether a signal is random or it has some correlations, so discriminate random and correlated data using the DFA. But there's another big thing in time series analysis, and this is to extract whether we have dominant frequencies in the data. The other 2 points we will discuss next time, but now I want to talk a little bit about how to get frequencies, the dominant frequencies in the time series, and this of course we do with a Fourier transform, right? Everybody knows what is a Fourier transform. So defined as GF integral over GT and an exponential. You can also calculate inverse Fourier transform. What is it doing? Basically, it assumes that a function g of t is represented by an infinite number of complex exponentials, or meaning sine and cosine functions, right? This is what, and the Fourier transform is dissecting this and telling you how much of this sinus with this frequency is present in the data, and that's the whole purpose of Fourier analysis. So when you do a Fourier transform, so your Fourier transformed is a complex function. You have an amplitude spectrum and a phase spectrum. You get this automatically nowadays with packages. You don't need to go into details. Also, the one that programs it later will talk a little bit more about this. But the important thing is that in a Fourier transform, you have a critical frequency. It's called Nyquist critical frequency. It means that when you have, for example, a signal with 2 Hertz, okay, a 2 Hertz signal, in order to detect this 2 Hertz signal, then you have to you can only detect this. So you sample with 2 Hertz, but you can only detect signals with 1 Hertz. Okay, so you want to measure when you have a sine wave with 1 Hertz, you need to sample this sine wave with 2 Hertz. So in order to identify it as a sine, you have at least to have 2 measurement points within 1 period in order to identify it as a sine wave. So you have this. So you have always to sample with twice the frequency than what is contained in the signal. And this is called the Nyquist theorem. So the critical frequency is half of the sampling frequency, or 1 divided by 2 times delta, where delta is the sampling rate. This looks familiar to what when you think about it? Where do you have this f times t equal to 1/2? Or you have x times p equal to 1/2. Uncertainty principle, right? And there is a relationship. I'm not going into. So where does the uncertainty principle comes from? From wave theory, right? You take wave theory and you get the uncertainty principle. There's a nice YouTube video where Sabine explains it in 5 minutes. It's interesting to watch, but just important for us is to keep in mind that we have this Nyquist theorem. This is just some mathematics, how you get from the Fourier transform that is on a continuous signal to a time series. That the time series is sampled equidistantly, so instead of doing a continuous Fourier transform, you have to do a discrete Fourier transform, and the most important is that you get Fourier coefficients. The Fourier coefficients now give you the kind of information to what extent a particular frequency is contained in your signal. Okay, this is what Fourier coefficients are doing. And let's look at this example. You have here a time series. In the time series, you have a 10 Hertz, 25 Hertz, 50 Hertz, and 100 Hertz contained. This is how it looks like. Okay, and now you do a discrete Fourier transform. And you get. So here, this is like the Fourier coefficients, and at particular frequencies. And we see here we get the peak at 10, 25, 50, and 100, right? What is the sampling frequency we see here? What is the sampling frequency? When you see such plot that goes up to 200 Hertz, so it means the maximum frequency that you can detect in the data is 200 Hertz. So with how much do I have to sample the signal to get here until 200 Hertz? 400, okay? So 400 Hertz is the sampling frequency. What happens when I sample with less? So what is here the sampling frequency? 160, right? So when I sample with 160, the maximum frequency that I can obtain is 80, right? Is this a problem?
There's no 60 in the equation.
It's a problem because I have 100 Hertz, right? So what happens? I get here the 10, right? I get the 25, I get the 50, but instead of getting the 100, I get here the 60. Why? Because it is kind of wrapped inside. Okay, so this is called aliasing. So I get here a peak at 60 that is actually not real. You know, I just get it because my algorithm would like to place it here, but it cannot, and then it's folded inside the 60. It's called aliasing, so it tells you that you always have to sample with high enough frequency in order to get a proper.
It's like mirroring where it should have been?
It's mirroring it.
It should have been 20 plus over there, so
yes,
it's 20
plus 20, so it goes minus 20, okay? You get this mathematically. Good. And the problem is that the Fourier transform does not preserve time information, so I can now take this 10, 25, 50 and 100 hertz, but not add it up at once, but I say, okay, in the first quarter I have 10 hertz, then 20, then 50 and then 100, and I do a Fourier transform and it tells me, okay, I have 10, 25, 50 and 100, but it's true, but I don't have any information when this happened, right? I would get the same power spectrum if I do the inverse. If I first start with the 100 and then with 50, and then you get the picture, right? So it doesn't give you any information when you had when one frequency was present in the data and when it was not present in the data. And what is an easy solution to this? You just do windows, right? You take a window. When you take here a window, you will detect exactly the 10 hertz. You do here a window, you detect the 25, and so on and so on. And this is called windowed Fourier transform. This is what you see here. You just take a window and then you recover. Now it's a 3D plot. Now you recover exactly where, at which window you had what frequency. Or you can plot it instead of in this way. You can say, I plot it as a spectrogram. Here's the frequency, here's the time, and the color code is the strength of the frequency, basically related to the Fourier coefficient, right? And if I take a signal like this, okay, like similar to gravitational waves, not quite, but it's a chirp signal, right? So you do a spectrogram of this. You see white noise, okay, nothing happening. Here you have a mixture of high frequencies, but not very well defined, and then you come to 35, and here you have a very prominent 5 hertz frequency oscillations. Frequency oscillation afterward it gets more broad. So this gives you an information about what kind of frequency was present in the data. And so that's basically it. Okay, so we covered how to get the random and correlated data and how to determine frequencies. And the one that will prepare the DFA and the one that will prepare the scripts for the Fourier transform will go more into the technical details. Any questions? Good, then thank you and see you next week. Thank you. Shabbat Shalom.